motivation for research. Now, how do you collide these heavy atomic nuclei? Well, you need a particle accelerator. And biggest game in town right now is the Large Hadron Collider at CERN, the European Center for Nuclear Research. And it's a fantastic facility, 27 kilometers in circumference. It crosses the border between Switzerland and France. So actually right beside the main compound of CERN, you have the border crossing where you go through on a regular basis. And there are several experiments, it's all underground, several experiments which have been devised to discover what happens if you smash these heavy atomic nuclei into each other, or two protons. Yes, that's the Higgs boson, which has been discovered and thus is utterly uninteresting. So we have the properties of the quark-gluon plasma. And one of the experiments, among three, which is measuring the properties of the quark-gluon plasma, is the ALICE experiment. It's huge. Weighs about 10,000 tons, 26 by 16 by 16 meters, and it has about a team of over 1,000 scientists working together to run this experiment and extract science from it. And there are two more experiments that can take heavy ion data, which are CMS and ATLAS, which were both built for the quest for the Higgs boson, which they were very successful with. Now, a typical collision, as reported by these experiments, looks like this. You have thousands of tracks of charged particles which come out of the collision vertex. And one of the main tasks of the experiments is to reconstruct all these tracks into particles, to figure out, each track stands for a particle. We need to characterize these particles. What is their charge? What is their mass? What is their momentum? Yeah, and some other properties they may have. And that gives us as complete a picture as possible for what happens in the collision. However, these particles are not the core of the gluons we are talking about. These particles are, the decay product of the quark-gluon plasma. So we are not measuring the quark-gluon plasma per se. We are measuring the ashes of its decay. So the way I can liken these measurements is think of an automobile crash test. Yes, you run your Mercedes against the wall to check whether it's safe. Now, because of some bug in your system, your high-speed cameras didn't turn on when the crash happened. And you only had this one Mercedes to wreck. Yeah. Okay. So now we have this debris field, and you need to know, what was the acceleration of my crash test dummies. So the only way you can figure that out is you go to this debris field, you measure out the debris field, and you try to reconstruct from that debris field what happened during the crash. That's essentially what we are doing in these heavy ion collisions. We measure the debris field, and we want to figure out what happened during the formation and lifetime of the quark-gluon plasma, which lived for a very short period of time. So this is an incredible data challenge. One of the reasons for the existence of grid computing, so to speak. We get about 15 petabytes per year of raw data. OSG Computing Grid has 170 computing centers across the world, which analyze about 25 petabytes of data and simulations annually. So the amount of data is compounded by the amount of simulation data which you have on top of that. And if you look at the vectors, yes, they record data at a rate of 15 gigabytes per second, which is actually too much even to handle. So there's some sophisticated hardware in there which reduces the data stream to about 1.25 gigabytes per second, which is then written onto file and distributed across the world for further analysis. So we are talking about huge demands in computation and data storage. This translates into certain challenges for theorists like myself who devise models of these heavy ion collisions. We need those models because, well, a collision takes 10 to the negative 24 seconds. That is too short for my crash test cameras to resolve. Yes, it has a characteristic length scale of 10 to the negative 15 meters. Too small for my cameras to resolve. So that's why I'm always just looking at the debris field. So that's the only thing I can actually measure. Yes. And so ultimately, what the experiments only measure is what we call the final state of the debris field. And my simulations are what make the connection between the debris field and what happened when the quark-gluon plasma was alive for that very brief period of time. Yes. So I have model calculations which try to simulate everything that happened in those 10 to the negative 24 seconds. And I try now to tune those models to what I observe in the experiment. And the parameters which I then extract from my tuning the models encode the science that I'm extracting, that I wish to learn. And so modeling and simulations are very, very important in our scientific process of extracting knowledge from those data. And well, these models are, of course, based on a variety of laws of physics and certain assumptions on how the quark-gluon plasma behaves. And I'm not going to go through all these formula, just to give you one idea. A very successful description is actually relativistic fluid dynamics. And as a matter of fact, the quark-gluon plasma was one of the triggers to actually develop a fully relativistic three-dimensional viscous fluid dynamics model, which hadn't existed before. So there's a lot of progress also in the computational sciences, which goes hand in hand with executing those experiments and trying to extract knowledge from them. Small disclaimer. Perhaps my friends in the weapons labs had such a hydrodynamic before, but obviously we didn't know about it. So, as far as regular science is concerned, it had to be reinvented. All right. Now, what is the computational challenge? I have a model, and these models take quite a bit of CPU time to run, and they have dozens of parameters in there which encode the science. At the same time, I have these huge data sets from the experiment, which I can sort of boil down into a variety of histograms or ways how to represent those data. Now, unfortunately, my model parameters don't linearly factorize and map onto the individual histograms into which I can organize my data. Yes, it is pretty much nonlinear, and each of my model parameters may affect 15 different data representations. Yes, so I cannot just individually tune one parameter after the other to a specific histogram or specific data representation. I have to do this all simultaneously. So I have a parameter space, which is 20-dimensional or so, for tuning my model, which produces an output on a scale of gigabyte or terabyte, which I now need to compare to data which is, on a petabyte scale. Obviously, this requires several things. It requires very clever techniques in data reduction. Yes, I really do not want to compare to a terabyte data set. Then secondly, it requires novel optimization techniques, from Bayesian statistics or Markov chain Monte Carlo methods. In physics, we would call this a metropolis algorithm. And this kind of data, science extraction from a model data comparison is a general problem. It's by no means restricted to MBI physics. You will encounter the same problem in atmospheric modeling as in meteorology. Modeling of supernova explosions in astrophysics. Yes, cosmological modeling. Any science where you use a complex computational model to compare to a large data set will encounter this same class of problems. Okay, so that's why statisticians are actually quite interested in developing these new techniques, is because they can be applied to multiple different systems. Okay, so what are our computational challenges? They're twofold. One is getting the CPU for our simulations, and then storing the data. And the Open Science Grid has really helped us with problem number one. So here's a little shopping list, depending on what kind of model I want to use, and the details of the models here are sort of irrelevant. I have a number of parameters. I need to repeat my model calculation sometimes tens of thousands of times, because these models are probabilistic in nature. So I need to run them 10,000 times and then average over the outcome of that model calculation to compare over what the experiments have measured, which is also usually represented in an average over many, many, many collisions which they record. And here's an estimate of how much a single simulation costs. And if I do my repetition and then vary my parameters over 10 values, yes, how much CPU time I would actually need. And this was done for available Core i7 or something, some CPU which is by now perhaps a few years old. Never mind. Ultimately, what we're talking about is for our knowledge data extraction. Basically, for one computational analysis, we are talking about 50 million CPU hours, which is, of course, something which your local little grid or cluster has a hard time delivering to you in a reasonable amount of time. Yes. And then so the Open Science Grid has been our salvation in this regard. This is our workflow. From our local desktops at Duke, we prepare the executables, input files. We configure our jobs such that they have an execution time of about 10 to 20 hours. That seems to be the sweet spot. If we configure them to run longer, like 40 or 50 hours, we get into trouble because then they don't just run through on an Open Science Grid node. They might get swapped out again and just sit around for a long time. So 10 to 20 hours works best. Then we use the Renzi Engage virtual organization to submit. Yes, it's basically based on Condor. And our jobs may run on anywhere between 1 and 100,000 of nodes independently. Well, so far we can't do 100,000, but in principle, for us it's just change a number in our submit script and back, off we go. And the Open Science Grid then does its magic, and we use the grid FTP protocol to write the data back from the individual compute nodes of the Open Science Grid over into a 100 terabyte array, which we have sitting at Duke in our server room. And then our compute cluster at Duke can combine the individual outputs which we receive into bigger files, run analysis on these output files, and perform visualization tasks. Now, here is just a snapshot of a week this summer where we were using the Open Science Grid. And so the person in red and the person in yellow are both in our group. And this is, I guess, for the Engage VO, the amount of CPU times which we were able to harvest. Each column, each bar represents 1 day, and you can see here the scale going up to 60,000. And so you can see that, that given week on average, we were able to harvest about 50,000 CPU hours per day, which for us is phenomenal. And it's frankly the only way how we can get that kind of computation analysis where we allocate, millions of CPU hours for a given analysis where we can get that through. And so the Open Science Grid was really, the technology that allowed us to take this step to actually execute this type of analysis, which prior to that just was not feasible. Okay, now the next challenge we have is data storage. Our models generate a bunch of output, and if we would want to store in order to reanalyze everything we need for our big analysis, for our calculation, we would end up with perhaps 1.5 petabytes of data. Now, a theory group, as we are, usually does not get any funding by the funding agencies for computer hardware because the Department of Energy assumes that that's something the universities provide as part of infrastructure. But show me any university in the world which is willing to provide a research group with 1.5 petabytes of storage. It doesn't exist. We are fortunate in the sense that we can do our analysis piecewise. So we can live with 50 terabyte or so of storage space where we collect our Open Science Grid data, we run the analysis, but then we just need to archive those 50 terabyte to make space for the next batch of 50 terabyte coming. For that, facilities in principle do exist. For example, at the National Energy Research Science Center at Lawrence Berkeley National Lab, there is a storage facility called HPSS, which has a theoretical capacity which is more than enough for us, has also huge disk spaces, decent throughput. The problem is just network bandwidth. How do we get our data from Duke to the HPSS? And the first time, I went to our systems administrator, Jimmy, who was sitting right there, and asked him, look, I have 50 terabytes on a regular basis. How do I shut that over to the HPSS at NERSC? What kind of network connections do I need? He just looked at me and said, use FedEx. So we didn't use FedEx because that put a certain strain on the drives, which we don't want to ship around. But frankly, FedEx has much bigger and better bandwidth for these kind of data transfer problems than anything you can get even from the highest performance data types which are available to this day. And that really leads us to the next challenge. In terms of CPU, I hope to have convinced you that if you do things right, then your friends at the OSG treat you well, then the amount of CPU you can get is pretty amazing. Yes. So in terms of CPU, all our needs essentially are being met by the Open Science Group. The big challenge for us is now, is there something like the Open Science disk, some kind of data storage, which we can tap into without really having to pay for it, which we have, like for the 100 terabyte array, which was expensive as hell, which we have sitting here in the basement at Duke. And is there a way to sort of access this data in a convenient way without clogging up all the networks in the United States, shuffling this around and shunting it to someplace? And of course, we are aware that sometimes it is cheaper to just regenerate data than to store it. But we haven't figured out yet what the best mix is in terms of analyze our data and just throw it away and then just go back to the Open Science Grid and then regenerate it if we need it again, versus how much do we need to archive in order to conduct our analysis and be on the safe side. All right, 4:30. That's it I wanted to say, and I hope